Welcome to the deep dive.
Yeah.
You know that feeling, right? Like you're constantly swimming in information, every click, every purchase, every interaction, leaving some kind of digital footprint. You can feel like we're just, adrift in this huge sea of data.
It's totally true. Data is just everywhere now, from your smart thermostat at home to, the massive systems processing your online shopping. It's kind of the invisible force behind almost every decision businesses make today.
And that's exactly why we're here today. We're taking a deep dive into that unseen world. We want to demystify how data is born, how it's meticulously organized, and where it ultimately lives.
Yeah, the whole journey.
Exactly. Our mission is to give you a shortcut to genuinely understanding this crucial backbone of our digital world. So you walk away not just like informed, but really getting the why behind the what.
Hmm.
We've pulled together a whole stack of insights specifically tailored for you, covering this intricate life cycle of data and the really ingenious ways it's stored and designed.
It is pretty ingenious when you get down to it.
So let's start right at the beginning. Why is data so essential? Not just for big companies, but in our everyday lives too. It feels like it's constantly being created. But what's its real core purpose?
Well, at its heart, data is critical for making decisions
Hmm.
and for auditing, for deep analysis. Across pretty much every sector you can think of.
Right.
And you're spot on. It is continuously generated, whether that's through transaction systems, the Internet of Things, or even, people manually typing things in.
Okay.
So to handle all of this responsibly, businesses generally follow what's known as the data life cycle.
The data life cycle. Okay, that sounds like quite a journey. Can you break that down for us?
Sure. Think of it as like the sequential path all business data takes.
Mm.
From its very first breath, its initial creation, through its active use, its long-term storage, and then finally its eventual disposal.
Gotcha.
There are basically 8 key stages: definition, capture, preparation, synthesis, analytics and usage, publication, archival, and purging.
8 steps.
Yeah.
Okay, so definition is step 1. That makes perfect sense. You have to figure out what data you even need to collect first, right?
Absolutely. It's all about clearly outlining the data a business requires and figuring out exactly where that data is going to come from.
Mhm.
Getting that clarity up front drastically increases the chance that what you collect will actually be, relevant to your goals.
Right.
And right after that comes capture or creation, which is simply how you actually get that data. And this is where it gets particularly interesting for companies because data can come from internal sources or external sources.
Internal versus external data. Okay, what's the main difference there, like fundamentally?
Well, internal data is generated directly by the company itself. This could be something manual, like an employee keying in a sales order.
Correct.
Or it could be fully automatic, like system logs, tracking, website activity. There are even semi-automatic methods, like using OCR optical character recognition, to turn a customer's PDF purchase order into a sales record that an employee then just verifies.
Right. Ah, I see. And external data, that sounds like it probably comes with a few more maybe headaches.
It certainly can, yeah. When data is acquired from an outside source, say market research data or public statistics, you definitely introduce added layers of complexity. Things around its integrity, its safety, copyright considerations.
Mm.
Companies often need to negotiate specific contracts about how it can be used, privacy rules, and there's frequently a cost involved too. It's often where the biggest legal and security issues can start if you don't manage it really carefully.
Okay, so once the data is captured, internal or external,
Yeah.
it can't just be immediately thrown into a report or something, can it? I'm guessing there's a vital preparation stage next.
What exactly makes data ready for use?
You've absolutely hit on probably the most crucial stage. Preparation is truly where data projects, well, they either soar or they sink.
Really? That critical? Oh, yeah. Before data can become genuinely useful for analysis, it needs to be rigorously enhanced for completeness and integrity. See, when data moves from one system to another, there's always a risk of loss or, manipulation.
Right, things getting dropped or mixed up.
Exactly. So we need to validate that the number of records matches the original source. We need to compare descriptive statistics, verify that field formats are consistent, and make sure character limits haven't, cut off important information.
So it's basically about making sure nothing got lost or scrambled in transit. What else goes into this preparation?
Well, a key component is data integration, especially when you're dealing with external data. If you're bringing in something like, say, real-time foreign exchange rates, your systems need to be set up to ensure that data flows seamlessly into your target database and that the updates keep coming in accurately and on time.
Makes sense.
Then there's the big one, cleaning data. This is all about assessing and actively improving its quality.
Cleaning data. Is it kind of like tidying up a really messy room, but for information? What sort of messes do you usually have to clean up?
That's a perfect analogy. It's very much like untangling, I don't know, 100 fishing lines all at once.
Okay.
You might need to remove unnecessary headings or subtotals that would just mess up analysis later. You've got to clean up pesky leading zeros or non-printable characters so everything's consistent. Make sure negative numbers are formatted the same way across all records.
Uh-huh.
A really common one is correcting inconsistencies, like when California is entered as CA, but also Cal or even Calif.
Mm-hmm.
You need one standard value.
Right, standardizing everything.
Exactly. And finally, ensuring consistent data types, like making sure dates are actually stored as dates, not just as random text strings someone typed in. Honestly, this stage is where most data projects either fly or fail. Think about it. People say 80% of a data scientist's time often goes just into this messy part.
Wow, 80%.
Yeah. Get it wrong, and your fancy multi-million-dollar AI initiative is basically built on quicksand.
That sounds like incredibly meticulous, painstaking work. And I imagine for really sensitive data, there's probably an extra layer of protection needed.
Oh, absolutely. Data encryption is paramount for sensitive stuff. It ensures integrity and security both when the data is traveling, in transit and when it's just sitting there in storage at rest. It's basically your digital vault.
Phew. Okay. So the data is finally clean, encrypted, integrated, ready to go. Then we move to synthesis. What does this step actually do for us? Sounds a bit abstract.
Synthesis acts as this crucial bridge between all that preparation and the actual usage. It's really about creating calculated fields that can significantly speed up analysis later on.
Calculated fields, like what?
Well, for example, if you have data points for gross sales and then sales returns, allowances, and discounts separately, you could synthesize a single net sales field right then and there.
Ah, okay, so you pre-calculate common metrics.
Exactly. While it's not always necessary for every single piece of data, it can be a really powerful way to make the data immediately more consumable for quicker insights down the line.
Okay, so once data is prepped and maybe synthesized, what happens next? It's finally ready for prime time, I assume, for people to actually use it.
That's right. The next stage is analytics and usage. This is where the data is finally put to practical use within the organization. So, for creating internal reports, informing internal decisions, that sort of thing.
Crucially internal.
Yes, exactly. This stage is purely for the company's internal benefit. The data isn't being shared with outside parties just yet.
But sometimes data does need to be shared externally, right?
Mm-hmm.
This feels like a really key turning point.
Yeah.
What changes when data leaves the company's sole control?
That's the publication stage. And you're right, it's a major shift. This involves sharing data outside the company, like sending monthly statements to clients or publishing financial reports for investors or maybe providing price quotes to customers.
Mm-hmm.
The crucial difference here is that once data is published, the company loses sole control over how that data will be used, or maybe shared further, or archived, or even purged by whoever received it.
Yeah, it's a big deal.
It is. This is precisely why you often hear about data breaches tied to third-party vendors. Your data security perimeter suddenly expands exponentially. You have to take immense care at this stage.
And what about the data's eventual, retirement? It can't just stay in those active high-performance systems forever, surely.
No, it definitely can't. That brings us to the last couple of stages, archival and purging.
Okay.
Archival is when data sets are moved from those active high-resource systems to more passive, maybe cheaper storage once they're no longer needed for immediate day-to-day operations. Think maybe financial data past its immediate analytical relevance.
Right, move it somewhere safe but out of the way.
Exactly. This frees up active storage resources, it can enhance system performance for the active data, and it reduces security risk by just limiting the exposure of older data. Ideally, you test the archive data for accuracy and make sure you can still access it before removing it from the active systems.
Makes sense. And purging is the final farewell, the true end of the line.
Indeed. Purging is the complete, final, and totally irreversible removal of data from a company's storage systems. It's absolutely critical here to make sure there's no legal or business requirement to keep the data before you hit delete.
Yeah, you wouldn't want to delete something you need later for legal reasons.
Absolutely not. But once that decision is made, the purging process ensures it's completely and irrevocably gone, like, shredding a physical document. No coming back.
So that's the full journey data takes, birth to death, basically.
Uh-huh.
But let's rewind a little bit. How is data collected in the first place? Are there different methods for just getting it into the system to begin this whole life cycle?
Yeah, good question. There are generally three primary methods of data collection we talk about.
Okay.
The first one is extract, transform, and load, or ETL as it's usually called.
ETL. Heard of that.
Right. This is typically used for existing data, whether it's internal or maybe external data you've acquired. It's extracted from its source system, then it's transformed, which means cleaned, standardized, maybe aggregated into a useful format. And finally, it's loaded into a new destination, like maybe a data warehouse, specifically for analysis. Think of it like taking ingredients from different fridges in your kitchen, prepping them all, and then putting them together in one bowl for a specific recipe you want to make.
Nice analogy.
While it involves steps that sound similar to capture, preparation, and synthesis, ETL is really a more specific process focused on gathering existing data to answer a particular analysis question.
Got it. So ETL is kind of like repurposing existing data for a new analytical job. What about when you need brand new data that doesn't exist yet?
That's where active data collection comes in. This is when you directly ask users for new information.
Okay, like surveys.
Exactly. Think about filling out a survey or registering for a service with an online form, or maybe participating in an interview where you provide your email, your phone number, your preferences. You are actively asking for and getting that data from the person.
Makes sense. And the third type, I've heard about things like, cookies tracking web usage or smart devices collecting info in the background. Is that part of this?
It is. That's the third method, passive data collection. This happens when companies gather information without getting direct, explicit permission from users for each specific piece of data collected in that moment.
Oh.
It includes things like tracking web usage via cookies, gathering timestamps of when users interact with the website, or data collected silently through Internet of Things devices, or even AI systems learning patterns.
Right, the stuff that happens behind the scenes.
hmm
Okay, so now that we know how data gets created and moves through its life cycle, the really big question is, where does it actually live?
hmm
How is all this data stored and, made accessible for all these different uses?
Yeah, data storage is fundamentally about retaining that information and making sure authorized users can get to it efficiently whenever they need it. There are several common types of data repositories, and each really has a specific purpose.
Okay, like what?
Well, first we have something called an operational data store, or ODS.
OD.
Right. This is basically a repository for transactional data, often pulled from multiple source systems. It frequently acts as an interim staging area, kind of a halfway house between a source system and maybe a data warehouse.
Okay.
It's designed for current, active data, and its contents are often overwritten pretty frequently as new transactions are processed.
Okay, so kind of a temporary, fast-moving holding spot for really active transactions.
Yeah.
What about a data warehouse? That sounds more permanent.
It generally is. A data warehouse is typically a very large, centralized repository used primarily for reporting and longer-term analysis, not really for active, real-time transactions.
Right.
It pulls historical data from various different enterprise systems or maybe from ODSs and integrates it all into a single comprehensive source. That makes it much easier to analyze trends over time, for instance.
And I've definitely heard of a data mart, too. How does that fit into this picture? Is it related to the warehouse?
It is. A data mart is basically like a smaller, more focused version of a data warehouse. It's often a specific subset of the main warehouse, tailored for a particular purpose, or maybe just a single department, like marketing or sales or logistics.
Ah, so different teams might have their own little slice.
Exactly. Different departments might extract their own data marts from the larger data warehouse to focus just on their unique analytical needs without getting bogged down by data from other parts of the business.
So specialized subsets. Now, a data lake,
Mm.
that sounds quite different. What's unique about that, and why would you use one instead of a warehouse?
A data lake is indeed quite distinct. Unlike data warehouses, it holds both structured and unstructured data. And critically, it holds it in its raw or original format.
Structured and unstructured. Okay.
Yeah. The key difference is that a data lake does not require you to define a data structure or schema before you dump the data into it. This is a sharp contrast with a data warehouse, which absolutely demands a schema be in place first so it can process things quickly. Imagine a giant digital, maybe junkyard is too harsh, but a vast storage pool where you just dump all your data, structured, unstructured, sensor data, logs, images, everything. And then you figure out what you want to build with it later. Data in a data lake isn't indexed or prepped until you actually decide what analysis you want to run, which offers incredible flexibility, especially for data scientists exploring new questions.
That's a really fascinating contrast in approach.
Hmm.
Interesting. And speaking of storage, we've seen just a huge evolution over the years, haven't we? Are companies still primarily using traditional physical storage, like servers in a closet? Or is everything moving to the cloud?
Well, traditionally, companies stored all their data on premises, on physical drives or servers located within their own data centers. And those physical repositories definitely still exist, especially for maybe highly sensitive data or older legacy systems. However, with the rapid advances in cloud computing and just the sheer exponential growth of data volume,
It's massive. It is.
maintaining those huge on-premises infrastructures has become incredibly costly and, frankly, cumbersome for many. Cloud-based storage offers really high scalability, letting companies store as much or as little data as they need, pretty much on demand. It gives them remarkable agility and often comes at a lower operational cost.
So, okay, we've got all this data and these different places to store it, cloud or on-prem. But how is all this data organized efficiently within these repositories? It can't just be a jumbled mess, can it? Especially with so much data coming in all the time.
You're absolutely right. It can't be a mess if you want to use it effectively. And one of the most efficient and effective methods for organizing structured data is to store it in what's called a relational database.
Relational database, okay.
Many operational data stores and even data warehouses are built upon this relational design concept. They're probably the most common way to store structured data because they offer some really significant core benefits.
What are those core benefits that make them so popular and effective?
Well, first, they aim to ensure completeness, that all the necessary data for a particular purpose is actually included.
Okay.
Second, and this is huge, they aim for no redundancy.
No redundancy. That sounds critical.
It is crucial because redundant data, well, it wastes storage resources, obviously, but more importantly, it creates multiple versions of the truth within an organization.
Yeah, that's bad.
Very bad. And it significantly increases the chances of data entry errors creeping in.
Hmm.
Relational databases also help with business rules enforcement, meaning they help ensure data follows predefined organizational standards. And finally, they significantly improve communication and integration across different business processes by providing this unified, consistent view of data across the whole organization.
That no redundancy point isn't just about saving disk space then. It's really about eliminating conflicting information and preventing costly mistakes that could ripple through the whole business.
Precisely. It's fundamental to data integrity.
Okay, no redundancy sounds fantastic, almost too good to be true in some ways. So how are these relational databases actually built to achieve that? What are their fundamental components, like the building blocks?
Right. They store data across a series of related tables, which are also sometimes called entities. A relational database, by definition, has to have at least two related tables.
Okay.
Think of separate tables for things like customers, sales orders, or employees. Each table contains attributes, which are basically the columns describing characteristics like last name or email address in that customer table.
Got it. Columns or attributes.
Yep. And each record or row contains all the information about one single entity, like one specific customer or one specific sales order.
Rows or records.
And the intersection of a column and a row is called a field, which holds a single piece of information, a single data value, like a customer's specific phone number.
Field holds the actual data point. And what about data types? I've heard of those being important.
Very important. Each attribute, each column has a designated data type. This specifies how the data is stored physically and how it can be analyzed later.
For example.
Well, you might have numerical for quantities that you want to do calculations on, or text for names or descriptions, or date time for timestamps.
Right.
And even within numerical, you might have types like int for whole numbers or decimal for numbers with fractions, which lets you do mathematical calculations. Char might be used for fixed-length strings, like a two-letter state code, while text, or varchar, is for variable-length strings, like a long product description.
Okay, so the type dictates what you can do with it. And the keys. I've definitely heard of primary keys and foreign keys. How do they tie all these tables together? That seems crucial for the relational part.
Database keys are absolutely essential. You nailed it. They uniquely identify each record, each row in a table, and they are what facilitate the relationships between related tables.
Okay.
A primary key, or PK, is a unique identifier that's required in every single table. Think of it like a student ID number or a sales order number. It's usually a single, often nondescriptive value that points to one specific record and only one.
Unique identifier. Got it.
Sometimes, though, a table might not have one single attribute that uniquely identifies each record on its own. In those cases, multiple attributes can be combined together to form what we call a composite primary key.
Okay, two or more columns acting as the unique ID together. And the foreign key then acts as the connector between tables.
Precisely. A foreign key, or FK, is an attribute in one table that serves as a primary key in another table.
Ah, the link.
Exactly. For example, customer ID might be the primary key in your customer table, but it would appear as a foreign key in your sales orders table. This links each sales order back to one specific customer without you having to duplicate all the customer's details, like their address and phone number, on every single order.
Right, that saves a ton of space and potential errors.
It does. And the same customer ID can appear multiple times in the sales order table, right? Because one customer can place many orders. That's how relational databases build their powerful, interconnected web of information. It's just like how your sales order form probably has a customer ID field to link back to all your customer details so you don't have to rewrite their address every single time you sell them something.
Makes total sense. But wow, with all these complex connections and relationships between potentially dozens or hundreds of tables, how do people keep track of what everything means? It sounds like it could get overwhelming really fast.
It absolutely could, and that's where a data dictionary becomes paramount. It's a type of metadata, which literally just means data about data.
Okay, data about data.
Right.
A data dictionary summarizes crucial information about the data within a database. It makes it far easier for database administrators to maintain the database and, crucially, for analysts and users to understand what the data actually means and how to use it correctly.
So it prevents misunderstandings.
Exactly.
Without it, a user could run an analysis thinking an attribute means one thing when it actually means something subtly different, leading to what we call material mistakes in their analysis, and ultimately leading to bad business decisions based on faulty data understanding.
So it's kind of like a highly detailed user manual just for the data itself, preventing those costly misinterpretations.
That's a great way to put it.
It typically contains everything from the attribute names and clear descriptions of what they represent to their data types, whether it's a primary or foreign key, whether a field is required or can be empty, any default values it might have, character limits, all those crucial details needed to work with the data effectively and avoid those dangerous misunderstandings.
Okay. Earlier, you mentioned no redundancy as this huge benefit of relational databases. It sounds amazing, but how do they actually achieve that? You mentioned normalization. What exactly is that?
Right. Normalization is a database design technique specifically aimed at reducing that data redundancy and also eliminating certain types of anomalies, those pesky inconsistencies that can crop up when data is duplicated across tables.
Okay.
It basically involves logically dividing larger, potentially less organized tables into smaller, more focused, interlinked tables. The whole goal is to ensure data is stored in the most logical, efficient, and consistent way possible.
It's like organizing things properly.
Think of it as tidying your digital closet really well so you never have to search for the same shirt in 3 different drawers. Everything has its single dedicated spot.
Nice. And I've heard of normal forms, like 1NF, 2NF, 3NF. Can you simplify those for us? I remember hearing a mnemonic once, something like the key, the whole key, and nothing but the key. Does that help?
That mnemonic is fantastic. It truly captures the essence of the main normal forms we usually aim for. Let's break it down using that.
Okay, great.
The key refers to the first normal form, 1NF. To be in 1NF, basically 2 things have to be true. First, each cell in a table must contain only one single piece of information, no lists or repeating groups within a cell. Second, each record, each row, must be uniquely identified, usually by having a primary key. So you have a key that points to a single distinct entry.
One value per cell and a unique ID. Got it. That's the key.
Right. Then, the whole key brings us to the second normal form, 2NF. This requires that the table is already in 1NF, and that all the non-key attributes in that table depend on the entire primary key.
The entire primary key.
Yes, this is especially important for tables that have a composite primary key. Remember, a primary key made up of multiple attributes combined. So for instance, imagine a table listing items on different sales orders. It might have a composite key of sales order ID and product ID. Now, the quantity ordered for that item clearly depends on both the specific order and the specific product, right?
Yeah, makes sense.
But what about the product name? Does that depend on the specific sales order?
No, it only depends on the product ID.
Ah, oh,
So to be in 2NF, product name shouldn't be in that sales order detail table. It should belong in a separate products table, linked by product ID, ensuring every non-key attribute relies on the whole key of its table, not just part of it.
okay. Depends on the whole key. Makes sense. So what's nothing but the key?
That defines the third normal form, 3NF. This requires the table is already in 1NF and 2NF, and that all non-key attributes depend only on the primary key, and not on any other non-key attributes in the same table. We call this avoiding transitive dependency.
Okay, example. Sure, let's say your sales order table had the sales order ID as the primary key, but it also included both the employee ID, who took the order, maybe a foreign key, and the employee name.
Right.
Well, the employee name depends on the employee ID, right? Not directly on the sales order ID itself.
Ah, I see. It depends on another non-key field.
Exactly. That's a transitive dependency. So to be in 3NF, employee name shouldn't be in the sales order table. It should reside only in the employee table, where employee ID is the primary key. This ensures all non-key attributes depend on nothing but the key of that table.
The key, the whole key, and nothing but the key. Got it.
And it's really important to remember these forms build on each other. You can't achieve 3NF unless you've already met the rules for 2NF, and you can't get to 2NF without meeting 1NF first. It's a progressive process.
So we've talked about the building blocks of data, the tables, the keys, and these rules like normalization for organizing it efficiently. But how do you actually plan all this out before you even start building the database? What are these data models and schemas I hear about? Are they like blueprints?
That's exactly what they are. You've hit on the critical planning phase for any robust data system. A data model is the high-level conceptual representation of the data structures you plan to have in your information system. Think of it as the abstract design, your initial vision or architectural drawing.
Okay, the big idea.
Right. A database schema, on the other hand, is the actual implementation blueprint. It's the precise set of instructions that tells the database engine exactly how to organize and store the data according to that model you designed. So yeah, the model is the plan and the schema is the detailed build specification for the database itself.
And these data models, I understand they're created in stages, right? Maybe for different audiences, getting more detailed as you go along.
Exactly right. There are generally three main types or levels of data models, each building on the last one with increasing levels of detail: conceptual, logical, and physical.
Okay, let's start with conceptual. That sounds like the 10,000-foot view, the big picture sketch.
The conceptual data model is indeed the highest level representation. It focuses just on the main entities, the key things about which you want to store data, like customers, products, orders, and their fundamental relationships to each other. It doesn't get into individual attributes or keys or how it's physically going to be stored. It's fantastic for communicating the overall design to business stakeholders or non-technical users because it's easy to grasp. You could literally sketch out just 5 main entities: customers, sales orders, products, employees, and maybe department, and draw lines showing how sales orders naturally relates to customers, products, and employees. Simple enough to draw on a whiteboard.
Okay, clear and simple for everyone. Then comes the logical model. What kind of detail does that add?
The logical data model builds significantly on the conceptual one. It adds all the attributes for each entity, and, crucially, it includes the primary and foreign keys that define the relationships.
Ah, so the keys come in here.
Yes. And it also adjusts for any entity relationship issues you might discover when you start applying those first or second normal form rules we talked about.
Right, making sure it follows the rules.
Exactly. For instance, while your sales orders table might not directly contain the product description because of 2NF, the logical model clearly shows how you can access that description via the product SKU attribute linking over to the products table. It provides much more detail about how normalization works and how tables connect, but it's still an abstract design. It doesn't specify how it's built, just what is structured.
Okay, more detail, adds attributes and keys, still abstract. And finally, the physical data model must be the absolute most detailed level, the real blueprint.
It is. The physical data model specifies exactly how the data will actually be stored in the database system you choose. At this level, entities literally become tables, and attributes become columns.
Okay, this is the nuts and bolts.
Totally.
Yeah.
It includes all the granular details you'd find in that data dictionary we discussed. The precise data types for each attribute, like INT, varchar50, date, Any character limits, whether a field is required, not any all, and any default values. This model is the complete blueprint for the actual database construction by the database administrators, and it's also crucial later for performance tuning once the database is up and running. You
Wow.
can literally see how everything builds from the conceptual, just boxes and lines, to the logical boxes with attributes and keys, to the physical, specific table names, exact column definitions, data types, everything.
So those are the blueprints for individual databases, often transactional ones. But what about specific database schemas for something like a data warehouse or a data mart? You mentioned those are designed more for analysis than daily transactions. Do they use different schemas?
That's a great question. While transactional databases often prioritize those highly normalized designs, like 3NF, to avoid redundancy, data warehouses and data marts commonly employ specific schemas optimized for reporting and analysis, often called star schema and snowflake schema.
Tag Snowflake, okay.
These schemas organize data around two main types of tables: fact tables and dimension tables.
Fact tables and dimension tables. What's the difference between those two and why these specific types for analysis?
Fact tables sit at the center and contain the numerical measures or metrics that you actually want to analyze, things like sales amounts, cost of goods sold, profit margins, quantity sold. They typically don't hold much descriptive text themselves.
Just the numbers.
Mostly just the numbers, and crucially foreign keys that link directly to the dimension tables. These foreign keys provide the context for the facts.
Okay, so the context comes from the dimension tables.
Exactly. Dimension tables contain all the descriptive or contextual data surrounding the facts. They describe the who, what, where, when, and maybe how related to the numerical facts in the fact table. Think dimensions like dates, product details, names, categories, customer demographics, store locations, geographical information.
Got it. Facts are the numbers, dimensions are the descriptions. So the star schema. It sounds pretty straightforward from the name.
It is the simplest and probably the most common approach for dimensional modeling. It has a central fact table, and then all of its associated dimension tables connect directly to it, like points on a star.
Ah, okay. So one central fact table and dimensions branching directly off it. Makes sense. What about the snowflake schema then? How is that different?
The snowflake schema is similar to a star schema in that it has a central fact table linked to dimensions. However, its dimension tables are further normalized.
Ah, normalization again.
Yep. This means the dimension tables themselves are broken down into multiple related tables instead of being one single, potentially large table per dimension. For example, a product dimension might be split into a product table, a product subcategory table, and a product category table, all linked together.
Sounds like it could get more complicated.
It can make the snowflake schema more complex to look at, yes.
Hmm.
It requires more tables and more foreign key joins to link everything together when you query it. However, it can sometimes save storage space by reducing data redundancy within the dimension tables themselves.
So more complex maybe, but it offers a trade-off then.
Yeah.
Potentially less redundancy in the dimensions.
Yes, exactly. While it's more complex in design, a snowflake schema might feel more normalized and can be more flexible, especially if your dimension data is very hierarchical or has lots of detailed subcategories. But honestly, both star and snowflake schemas are generally designed to be easier for business users to understand for reporting purposes compared to a highly normalized transactional schema. They also tend to work exceptionally well with modern business intelligence tools like Tableau or Power BI.
So they're optimized for querying and reporting.
Pretty much. These schemas are often a deliberate trade-off. You might introduce a bit of controlled data redundancy back into the overall data warehouse structure compared to a perfect 3NF design.
Ah, so they're less normalized in a way.
Often, yes, particularly the star schema. They are denormalized to some extent compared to a transactional system. This can lead to some data redundancy and maybe losing that perfect one version of the truth sometimes. But you make that trade-off for the sake of faster, simpler reporting and analysis, which is the primary goal of a data warehouse or mart.
What an incredible journey we've taken today. Seriously, from the very first spark of an idea for what data is needed, through its meticulous definition, capture, preparation, and synthesis,
Yeah, the whole life cycle.
all the way to its powerful analytical use, external publication, and eventual archival and purging. And then we dug into where this data actually lives, exploring operational data stores, data warehouses, data marts, and even data lakes, whether they're on-premises or in the cloud. We really unpack the ingenious design of relational databases too, with their tables, keys, and the cleverness of normalization using those normal forms.
And finally, the blueprints, the data models and schemas that bring it all to life, including those star and snowflake schemas for analysis.
You've just gotten a really powerful shortcut, I think, to truly understanding the backbone of modern information systems. You can now hopefully appreciate the why behind the what when you hear people talking about data.
Yeah.
All this unseen structure and all these processes ensure that the vast amounts of information we generate every single day can actually be turned into meaningful, reliable insights that, well, that drive our world.
So what does this all mean for you, our listener, as you just go about your digital life day to day?
Well, if we try and connect this to the bigger picture, maybe consider how our increasing reliance on that passive data collection we talked about.
Right, the cookies, the IoT devices.
Exactly. How that might be subtly reshaping our understanding of privacy in this digital age. Given how absolutely central data integrity and structure are to making data useful, as we've discussed,
Mhm.
it really raises an important question for all of us, I think. As more and more data is collected without our active moment-to-moment consent, how do we ensure both the quality and integrity of that data and the safeguarding of individual privacy? It's a tricky balance.
That is a powerful thought to ponder as you navigate your digital life. Next time you click a link or maybe a notification pops up, or even just check your weather app, perhaps take a moment to appreciate the invisible, intricate journey of data happening behind the scenes. Keep exploring, keep questioning, and join us next time on The Deep Dive.